There are limits to how things can move. Limits determined by the law of conservation of energy. It says, the total energy is neither increased nor decreased in any process. We see this when non-conservative forces transfer energy into or out of a system, and when conservative forces transfer energy within a system. The net work done on a system is the sum of the work done by the conservative and non-conservative forces. We saw earlier that net work was equal to the change in kinetic energy, and that conservative work decreases potential energy. So the work done by non-conservative forces to transfer energy into or out of a system is equal to the change in kinetic and potential energy. How this affects motion depends on whether work is done to transfer energy. If only conservative forces act, the work done by non-conservative forces equals zero and mechanical energy is conserved. When non-conservative forces do act, mechanical energy is not conserved. Forces that transfer energy out of the system are called dissipative forces. Usually there is some form of friction and reduced mechanical energy in the form of thermal energy, either to the object or to the environment. The thermal energy produced is equal to the work done by friction. So in both cases, energy is ultimately conserved. So let's take a look at the skater. Right now the system has zero energy. So how do we add energy to the system? So I can come along and provide a non-conservative force and lift the skater up. Now the skater has a certain amount of potential energy. I have friction turned off, so I'm going to let the skater go. The skater is going to move back and forth, right? There's no non-conservative forces acting, there's no friction. So the total energy here is staying the same, and the potential and the kinetic are just swapping back and forth as she goes up and down. Right? It's like a perpetual motion machine. So I did positive work to add energy to the system. Right here, we're showing mechanical energy being conserved. If I add friction, now friction is going to do negative work to remove mechanical energy from the system. Right, so you can see that the potential and the kinetics still going back and forth, but the overall amount is decreasing, while the amount of thermal energy, which is added to the track and to the skateboard, is increasing. But the total energy remains the same. It's the sum of this thermal energy plus these back and forth kinetic and potential energies. Let's look at a question. At the water park, Katie slides down each of the frictionless slides shown. At the top, she's given a push so that she has the same initial speed each time. At the bottom of which slide is she moving the fastest? So let's apply the law of conservation of energy. Since the slides are frictionless, the work done by non-conservative forces equals zero and mechanical energy is conserved. So any change in kinetic energy corresponds to an equal and opposite change in potential energy. So in all three slides, the height is the same, so the change in potential energy, the decrease in potential energy will be the same, so they'll all have the same increase in kinetic energy. So as a result, her speed is the same at the bottom of all three slides. Let's look at a couple example problems. A roller coaster has a velocity of 25 meters per second at the bottom of the first hill. How high was the hill? So let's apply the law of conservation of energy. In this case, there's no friction, or at least we're ignoring friction, so the work done by non-conservative forces equals zero. So the increase in kinetic energy plus the decrease in potential energy has to equal zero. So mgy equals 1/2 mv squared. Our masses will cancel. And if we rearrange for y, we have y equals v squared over 2g. So y is going to be 25 squared over 2 times 9.8, or 32 meters. 1,500 kilogram car moving at a speed of 20 meters per second comes to a halt. How much work was done by the brakes? So apply law of conservation of energy. In this case, there is work done by non-conservative forces in the form of friction, but because it's just moving on a road, there's no change in height. The gravitational potential energy, the change in potential energy rather, is just going to be zero. So the work done by non-conservative forces is going to equal the decrease in kinetic energy. So it's negative 1/2 1500 times 20 meters per second squared. So we have negative 300,000 joules of non-conservative work done to bring the car to a stop. For number 3, an arrow is fired vertically upwards by a bow and reaches an altitude of 134 meters. Find the initial speed of the arrow on the ground level. So again, we're ignoring friction and we're going to apply the law of conservation of energy. So the work done by non-conservative forces equals 0. So 0 is going to equal the decrease in kinetic energy plus the increase in potential energy. So we can say that 1/2 mv squared equals mgy. Our m's cancel again. We rearrange for v, and we get v is equal to the square root of 2gy. So 2 times 9.8 times 134, we take the square root, and we get 51 meters per second.